properties. Hi everyone. Today, we begin our journey into the fascinating world of quantum theory and technologies. Before diving into the quantum domain, we must first appreciate the foundation built by classical physics. Classical physics assumes determinism. If we know the present, we can predict the future precisely. It also assumes continuity, meaning energy changes smoothly, and objective reality, where things exist whether or not we observe them. These ideas shaped Newton's mechanics, thermodynamics, and Maxwell's equations, which explained almost everything in our visible world, from how a pendulum swings to how electricity lights up your home. However, when scientists began probing atoms and subatomic particles, these assumptions began to fail. This is where quantum theory entered, offering a revolutionary perspective on how nature truly works at the smallest scales. Successes of classical physics. Classical physics was remarkably successful for centuries. It accurately predicted planetary motion, which allowed astronomers to forecast solar eclipses centuries in advance. Engineers used it to design bridges that could withstand heavy loads, steam engines that powered the Industrial Revolution, and electricity that illuminated entire cities. Even today, when you use Google Maps, the satellites that calculate your location rely on Newton's classical orbital mechanics. In our daily life, when we drive a car, ride a bicycle, or see light through a prism, all of this can be explained by classical laws. In short, classical physics gave us a complete understanding of the macroscopic world, the world visible to our eyes. Breakdown of classical physics. Despite its immense achievements, classical physics could not explain certain phenomena at the atomic and subatomic scale. For example, the blackbody radiation problem suggested that heated objects should emit infinite energy at high frequencies, an absurd prediction known as the ultraviolet catastrophe. Then there was the photoelectric effect, where light shining on a metal could eject electrons, but only if the light's frequency was above a certain threshold, regardless of intensity, something classical physics failed to explain. Another puzzle was the stability of atoms. According to classical electromagnetism, electrons should spiral into the nucleus while emitting radiation, yet atoms remain stable. These anomalies could not be brushed aside, and they hinted at a deeper truth beyond classical laws. The scientific world was forced to think differently, leading to the birth of quantum mechanics. Generation of quantum ideas. To overcome these failures, scientists began exploring new ideas at the dawn of the 20th century. Max Planck, in 1900, proposed that energy is not continuous but comes in tiny packets called quanta. This bold idea was revolutionary. It suggested that nature itself is quantized at the smallest level. Albert Einstein extended this by explaining the photoelectric effect using photons, or light particles. These breakthroughs opened the door to reimagining the universe not as a deterministic, continuous machine, but as a place governed by probabilities and discrete states. Think of it this way. Instead of a dimmer switch where brightness changes smoothly, quantum mechanics is more like a staircase. Energy changes step by step. This conceptual shift marked the beginning of a completely new scientific framework. Concept of wave-particle duality. One of the most fascinating discoveries was wave-particle duality. For centuries, scientists debated whether light was a wave or a particle. Classical physics described light as a wave, explaining reflection and refraction beautifully. But the photoelectric effect showed it could also behave as particles called photons. Later, scientists found that even matter, like electrons, exhibited both particle and wave-like properties. This was shocking because, In our daily lives, we never see a football behaving like a ripple on water. But at the atomic level, electrons, protons, and photons follow this strange duality. This idea challenged the sharp divide between wave theory and particle mechanics, forcing physicists to rethink the very nature of reality. Generation of quantum mechanics. From these discoveries, a full-fledged theory called quantum mechanics was born. It was no longer deterministic but probabilistic. Schrodinger developed his famous wave equation in 1926, which described how particles like electrons behave as probability waves. Heisenberg, around 1925, developed matrix mechanics, and Max Born introduced the interpretation that these wave functions represent probabilities, not certainties. Perhaps the most. Classical mechanics versus quantum mechanics. Classical mechanics and quantum mechanics differ in profound ways. Classical physics treats energy as continuous, while quantum physics reveals it is quantized, meaning particles can only have discrete amounts of energy. Imagine climbing a hill. In classical terms, you could stop at any height, but in quantum terms, you can only stand on specific steps of a staircase. Quantum mechanics also introduced probability, where outcomes are not definite until observed. This new framework was necessary to explain the microscopic world. Importantly, classical mechanics wasn't discarded, it still works wonderfully for the macroscopic world, cars, planets, and buildings. But when we zoom into the atomic scale, only quantum mechanics can explain what we see. Classical versus quantum. This comparison highlights why quantum mechanics was essential. Classical physics works like a predictable clock, where every gaze movement determines the next. But quantum mechanics is like rolling dice, you can predict the probability of outcomes, not exact results. For instance, when predicting planetary motion, Newton's laws are perfect. But when explaining how electrons orbit nuclei or why semiconductors work, only quantum physics provides answers. This shift shows us that classical and quantum mechanics are not enemies, instead, they complement each other. The classical rules dominate our visible world, while quantum rules govern the hidden microscopic universe. Applications of quantum physics. Quantum theory is not just theoretical, it powers much of modern technology. Semiconductors and transistors, the heart of every computer and smartphone, rely on quantum principles. Lasers, used in barcode scanners, DVD players, and even surgery, are products of quantum mechanics. In healthcare, MRI machines use quantum physics to produce detailed images of our bodies. The cutting-edge field of quantum computing promises to solve problems that classical computers could never handle, like cracking encryption codes or simulating complex molecules for drug discovery. Even the internet and secure communication are being revolutionized by quantum cryptography. So, when you unlock your phone, stream a video, or undergo a medical scan, remember it's quantum mechanics at work. Summary. Let's summarize what we've learned so far. Quantum mechanics was not born to destroy classical physics but to extend it. It arose because classical laws failed to explain certain phenomena. Quantum theory introduced concepts like quantization, probability, and uncertainty, which helped solve those mysteries. The result was a paradigm shift, not just in science, but also in philosophy, as it changed how we think about reality itself. Remember, classical mechanics still works perfectly for the macroscopic world, cars, planets, bridges. But when it comes to electrons, atoms, and photons, quantum mechanics is the ultimate guide. This dual framework is what makes modern physics complete. Principles of quantum mechanics. Quantum mechanics is the science of the atomic and subatomic world, and it operates under principles that often sound strange compared to classical physics. There are 4 core ideas. First, superposition, which means a quantum system can exist in multiple states at the same time until measured. Second, entanglement, where two particles become mysteriously linked so that a change in one instantly affects the other, even across large distances. Third, the uncertainty principle, which tells us that we cannot know everything about a particle's position and momentum simultaneously. Finally, wave-particle duality, where particles like electrons and photons can behave both like solid objects and waves. These principles are not just abstract concepts, they form the foundation of technologies like quantum computers, secure communication systems, and advanced medical imaging. Superposition concept. To understand superposition, let's think beyond our everyday experiences. In the classical world, a coin is either heads or tails when flipped. But in quantum physics, before we look, the coin can be in a state of both heads and tails at the same time. This is what we mean when we say a system is in a superposition. At the atomic level, electrons do not spin in one fixed way, they can exist in multiple possible states simultaneously. Only when we observe or measure them do they collapse into one definite outcome. This idea is so counterintuitive because our daily experiences don't prepare us for objects being in two or more states at once. Yet, this is exactly how quantum particles behave. Superposition, real and conceptual examples. Let's make superposition clearer with examples. Conceptually, imagine a light switch that can be both on and off at the same time. In the classical world, that's impossible. But in quantum systems, it is normal. For a real scientific example, an electron can be in a superposition of spinning clockwise and counterclockwise until we measure its spin. Another way to think about this is in computing. In classical computers, bits can be 0 or 1, but in quantum computers, qubits can exist in a superposition of both 0 and 1. This allows quantum computers to process an enormous number of possibilities simultaneously, giving them a huge advantage over classical machines. Superposition significance. Superposition has profound implications. In quantum computing, it allows systems to explore millions of combinations at the same time, making them capable of solving problems classical computers might take centuries to crack. It also challenges our logical understanding of the world. To explain this strangeness, Schrodinger proposed his famous thought experiment: imagine a cat inside a sealed box with a mechanism that can kill it based on a quantum event. Until you open the box, the cat is both alive and dead at the same time, a superposition of states. This illustrates that in quantum mechanics, outcomes are not fixed until observed. Such ideas may sound philosophical, but they directly shape modern technologies, from secure communication to advanced drug simulations. Entanglement concept. Another cornerstone of quantum mechanics is entanglement. When two or more particles become entangled, their states are interconnected in such a way that knowing one particle's state immediately gives information about the other, no matter how far apart they are. This means a change in one particle instantly affects the other, even across galaxies. Einstein himself called this spooky action at a distance. But experiments have repeatedly shown that entanglement is real. Think of it like having two magical dice. No matter how far apart they are, if one shows a 6, the other instantly shows a specific, linked number. This kind of correlation goes far beyond anything classical physics can explain. Entanglement conceptual example. To make entanglement more relatable, imagine flipping two coins at the same time, but with a strange rule: they are always opposite. If one coin lands heads, the other must land tails, even if it is on another planet. This is how entangled particles behave. Their states are not independent but deeply connected. This example shows why entanglement is so puzzling. It breaks our classical intuition about distance and independence. In real experiments, entangled photons have been separated by kilometers, yet they still instantly respond to changes in each other's states. This shows that quantum information is not bound by the same rules as everyday physical objects. Entanglement significance. Why does entanglement matter? First, it challenges our classical understanding of space and time. But more importantly, it enables revolutionary technologies. In quantum cryptography, entanglement ensures that communication is unhackable, since any attempt to measure or intercept the particles would disturb their state and reveal the intrusion. Another application is quantum teleportation, where the state of one particle can be transmitted to another at a distant location without physically moving the particle itself. In laboratories, entangled photons have been shown to maintain their correlations over many kilometers. These findings prove that entanglement is not just a theoretical curiosity, but a powerful tool for next-generation communication and computing systems. Uncertainty principle concept. The uncertainty principle, introduced by Werner Heisenberg, is one of the most profound aspects of quantum mechanics. It states that we cannot precisely measure both the position and momentum of a particle at the same time. The more accurately we know one, the less accurately we can know the other. This is not due to experimental error, but is a built-in feature of nature. Imagine trying to measure a tiny, fast-moving object with a flashlight. The light you use to see it disturbs its motion, meaning your act of observing has already changed the system. This principle breaks the classical belief that the future can be predicted with certainty if the present is known. Uncertainty principle conceptual example. Think of the uncertainty principle with a simple analogy. Imagine you are trying to track a hummingbird. If you focus closely on its exact position, say, which flower it is sitting on, you lose track of its speed. If you measure how fast it is flying, you can no longer pinpoint exactly where it is. This is similar to how electrons behave in quantum mechanics. You cannot know both their exact location and momentum simultaneously. Uncertainty principle significance. The uncertainty principle has deep consequences. It sets fundamental limits on what can be known about a quantum system. For example, it explains why electrons don't simply fall into the nucleus of an atom. The uncertainty in their momentum gives them a sort of quantum cushion, preventing collapse and making atoms stable. This principle also shatters classical determinism, the idea that the future can be predicted exactly if we know the present. In quantum mechanics, we can only predict the probability of outcomes. This has led to powerful technologies, like the corrections applied in GPS satellites, which rely on quantum effects to maintain accuracy down to fractions of a second. Wave-particle duality concept. Now let's return to wave-particle duality, one of the most puzzling features of quantum mechanics. Particles like electrons and photons can behave both as waves and as particles depending on how we observe them. For example, light behaves like a wave when it produces interference patterns, but like a particle when it ejects electrons in the photoelectric effect. For example, imagine throwing a baseball and finding that sometimes it splashes like water and other times it bounces like a solid ball. The nature of particles is not fixed, it depends on how they are observed. Wave-particle duality, conceptual example. To simplify wave-particle duality, think of a ripple on water and a marble. In classical physics, they are completely different. One is a wave, the other is a particle. But in quantum physics, entities like photons and electrons can behave like both. Imagine tossing a stone, but instead of choosing one behavior, it sometimes acts like a wave spreading out, and sometimes as a solid particle hitting a target. It has been demonstrated in experiments where electrons, which we normally think of as particles, create interference patterns like waves when passed through slits. This dual nature is at the heart of quantum mechanics. Wave-particle duality evidence. The strongest evidence for wave-particle duality comes from the famous double-slit experiment. When particles like electrons or photons are passed through two slits, they create an interference pattern on the screen behind, as if each particle traveled through both slits simultaneously like a wave. But when we try to observe which slit they went through, the interference pattern disappears and they behave like particles. Summary. To summarize, we've explored the four pillars of quantum mechanics: superposition, entanglement, uncertainty, and wave-particle duality. Each of these ideas defies classical intuition, but is supported by experimental evidence. Together, they form the foundation of modern quantum science and its applications. Superposition allows systems to exist in multiple states at once, entanglement links particles across space, uncertainty sets limits on what can be known, and wave-particle duality reveals the dual nature of matter and light. These principles are not isolated concepts, but interwoven ideas that reshape our understanding of the universe. Where we use these ideas. Now, let's connect theory to practice. Quantum principles power many modern technologies. Superposition is used in quantum computing, allowing qubits to process multiple states simultaneously. Entanglement is the backbone of quantum encryption, which promises unbreakable communication security. Wave-particle duality enables tools like electron microscopes, which give us images far more detailed than traditional microscopes. And the uncertainty principle is vital in corrections for atomic clocks and GPS systems, ensuring pinpoint accuracy in navigation. Far from being abstract, these principles are at work in your smartphone, in hospitals, in national security, and in scientific laboratories across the world.